Today's topic is a very important one in lots of different areas, biochemistry, particularly in medicine, and also in other branches of chemistry. It's about buffers. And we'll define buffers later on and explain how they work. It's really not that complicated, but it can be a little bit tricky until you catch on to what the basic idea is. But we have the ground covered that we need to understand buffers at this point, and the stage is set for learning that. We're going to start out with 3 quiz-kin questions, beginning with this one. The Ka of HNO3 is 6 times 10 to the minus 4th. We want to know what is the concentration of OH minus in a 0.1 molar solution of NaNO3. So not the acid, but a salt that contains an anion from the acid. Stop the video and give this a try. A rice chart will probably be part of your solution. I'll bring you an answer in a little bit and then a solution. First of all, let's examine what happens when we put sodium nitrite in water. Because it's a group 1 salt, it's going to dissociate fully to give nitrate ions. So if I have a 0.100 molar solution of NaNO2, I will also have a 0.100 molar solution of NO2 1-, because the stoichiometry is 1:1 and it's a complete dissociation. So now let's set up our rice chart. The reaction here is going to be NO2-, which is a weak base, because it's the conjugate base of HNO2, is going to react with water and reversibly produce hydroxide ions and HNO2, the conjugate acid of NO2 1-. The initial concentration is 0.100. Water concentration we don't care about. Hydroxide and nitrous acid will both be 0 initially. And then the change is 1:1 stoichiometry. So we lose X moles of each reactant and we gain X moles of each product. So at equilibrium, 0.100 minus X is the base concentration. Water we don't care. And hydroxide and HNO2 are both going to be X's. So to find the concentration of OH minus at equilibrium, we need to solve for X. Well, Kb for this reaction is going to be concentration of OH minus times concentration of the conjugate acid divided by the initial concentration of the NO2 minus, and water is not in this expression. And this would be equal to X squared divided by 0.100 minus X. Now the problem here is that we do not have the value of Kb for NO2. And if you try and look up Kb for NO2 1-, you will not be able to find it probably. However, we can find the Ka for the conjugate acid. And since the relationship between conjugate acid and base is that Kw is the product of Ka and Kb, Kw divided by the Ka for HNO2 will be equal to Kb for NO2 1-. So we'll put numbers to this. Kw 1.0 times 10 to the minus 14th. And if you look up nitrous acid's Ka, you will find out that it's 6.0 times 10 to the minus 4th. You can get that from a lot of internet sources or your textbook probably. And when you work the arithmetic out here, this comes out to 1.7 times 10 to the minus 11th. That's Kb. So plugging that into our chart here, 1.7 times 10 to the minus 11th is going to be equal to X squared over 0.100 minus X. And because 10 to the minus 11th is a really small number, we can make the valid assumption probably that this is approximately equal to X squared over 0.100 to simplify our math. So X, which is going to be the concentration of OH minus, is equal to the square root of 0.100 times 1.7 times 10 to the negative 11th. And that comes out to 1.3 times 10 to the minus 6th. And that's our answer. This next problem doesn't give us an actual acid. It just gives us a generic weak diprotic acid. The pH of a 0.100 molar solution of this acid is 3.68, and we're supposed to determine what is Ka for the acid. So here's our diprotic acid, H2A, and it's going to dissociate. Its first ionization is going to be H plus HA 1-. And we have to find out what Ka is for this acid. Now, since most of the H plus is going to come from the first ionization, Ka1 is what we're really looking for here. And that's going to be equal to concentration of H plus times concentration of HA minus divided by the initial concentration of the H2A. Let's set up a Rice chart. We already have the reaction in place. Initial concentration, this is a 0.100 molar solution. If we start out before ionization, there are no products. The change is 1 to 1, so minus X plus X and plus X. At equilibrium, we now have 0.100 minus X and then X. This is becoming a really common pattern in a lot of these Rice charts. If you have one-to-one stoichiometry, some of you are to the point now where you can probably skip the Rice chart altogether and go straight to the Ka expression, because we know that Ka now is going to be equal to X squared over 0.100 minus X. So if we can find out what X is, then we've got it made. And in fact we can, because X is the equilibrium concentration of H plus. And that's going to be equal to 10 to the minus pH at equilibrium. So in this case, 10 to the minus 3.68. 10 to the minus 3.68 is 2.1 times 10 to the negative fourth. And so we'll plug that into this equation and find our answer. So it's going to be 2.1 times 10 to the minus fourth squared over 0.100 minus 2.1 times 10 to the minus fourth. And you could probably leave that off in the denominator because it's not going to make any difference since it's so much smaller than 0.1. You do your arithmetic, you are going to find that Ka is equal to 4.4 times 10 to the negative seventh for this weak acid. This next quiz isn't going to be quantitative, at least not at first. We're supposed to classify solutions of these salts as acidic, basic, or neutral. Remember how we do this is we look at the cation and we look at the anion separately and then make our determination. So stop the video and give this a try. I'll bring you an answer in a bit. Well, let's look at NaNO3. We'll split it up into cation, which is Na plus, and anion, which is NO3 1 minus. Na plus comes from a strong base, NaOH, and so that means it contributes to a neutral solution. The NO3 comes from a strong acid, and so that means it also contributes to a neutral solution. So the overall result is NaNO3 solution would be neutral. Next one, KCN. K plus, just like Na plus, is the cation from a strong base, so that contributes to a neutral solution. Cn minus is not from a strong acid, so it wouldn't be neutral. It's not starting with H, so it's not an acidic anion. So Cn minus is in fact a weak base, and it's the conjugate base of cyanic acid. And so if that contributes to a basic solution and K plus contributes to a neutral solution, the net result is it's going to be a basic solution. Next one. Zn2 plus is the cation and Cl minus is the anion. Zn2 plus as a cation has only two choices. It can be neutral because it's from a strong base, and that's not the case here because it's not calcium, strontium, barium, or a group 1. So that means it has to be acidic. Cl minus. Well, this is the anion from a strong acid, so that means it's a neutral solution contributor. And if I have acid plus neutral, the net result is going to be acid. The last one, NH4 1 plus is the cation, and F1 minus is the anion. Well, NH4 1 plus is not the cation from a strong base, so that means it's going to contribute to an acidic solution. Fluoride is the conjugate base of HF, so that will contribute to a basic solution. So in order to make this determination, we have to compare the Ka for NH4 and the Kb for F minus. So to solve this first problem here, it's really only thought of as the conjugate acid of ammonia. So Ka for NH4 here is going to be equal to Kw divided by the Kb for ammonia. So that's 10 to the minus 14th divided by the Kb for ammonia, which is 1.8 times 10 to the minus 5, and that comes out to 5.6 times 10 to the minus 10. Now we also need to find the Kb for F minus, and we're not going to find that in any chart because it is usually thought of as just the conjugate base of HF. So we'll take Kw and divide it by the Ka for hydrofluoric acid. So Kw is 1 times 10 to the minus 14th And the Ka for HF you can look up, and it's 7.1 times 10 to the minus 4th. So if we do this arithmetic, we find that it's 1.4 times 10 to the negative 11th. Now if we make a comparison, Kb is 10 to the minus 11, Ka is 10 to the minus 10, so that means Ka is bigger than Kb, so that's telling us that this will be ultimately an acidic solution. Well, let's get started with the common ion effect, and that will help us lay the last of the groundwork that we need to understand how buffers work and what a buffer really is. The common ion effect occurs when the same ion, a common ion, is provided in an aqueous solution from two different sources. And the overall effect is that it changes the concentrations at equilibrium of products from what they would be if that ion wasn't present from the second source. Probably best to understand this by example. So let's take a look at this example. What is the pH of a mixture made by adding 1 molar acetic acid to a 1 molar sodium acetate solution? So acetic acid provides H pluses, but sodium acetate, if you think about this, it's NaC2H3O2. That's going to be an aqueous, completely soluble salt because it's a group 1, so it's going to give you Na pluses and acetate ions. So acetic acid gives you acetate ions because it does this, HC2H3O2, decomposes reversibly to give you H plus and C2H3O2 1 minuses. Produces acetate ion. That also produces acetate ion. This is a common ion. So we'll look at the common ion effect here. And notice that the stoichiometry with acetic acid and sodium acetate is 1 to 1. So a 1 molar solution of sodium acetate will give us a 1 molar concentration of acetate ion because it completely dissociates. So let's look at what would happen if we had HC2H3O2 dissociating to give us C2H3O2 1 minus and H plus. But here what we know is the initial concentration of acetate isn't 0 like it would be typically when we set up these ice charts. So our concentration of acetic acid is 1.0 molar. But our concentration of acetate before we even start dissociating is also 1.0 molar because we had a 1 molar solution of sodium acetate mixed together. But there is no H plus. Our change is simple, 1 to 1. At equilibrium, we'll have 1.0 minus X and 1.0 plus X, and then we'll have X for H plus concentration. Well, the Ka for acetic acid is 1.8 times 10 to the minus 5th. And in the numerator, we're going to have concentration of acetate ion, which is now 1.0 plus X, times concentration of H plus, which is X, divided by the concentration at equilibrium of acetic acid, which is 1.0 minus X. And because 10 to the minus 5th is small, we're going to assume that this is the same as 1.0 times X divided by 1.0, and that is X. So X, which is our H plus concentration at equilibrium, is equal to Ka in this case, which is 1.8 times 10 to the minus 5th. And that assumption that we made that the X's were okay to leave out is all right because 1.8 times 10 to the minus 5th is much smaller than 1. So what is the pH? Well, based on this, pH is going to be minus the base 10 logarithm of 1.8 times 10 to the minus 5th, and that's equal to 4.74. Now, why don't we do a comparison to find out what the common ion effect is? Let's pretend that we had this same solution of acetic acid, and it was going to dissociate, just like it normally would, into acetate ions and H+, but now we don't have the common ion in there. So initially we'd have a 1.0 and a 0 and a 0. The change is still 1 to 1. At equilibrium then, we have 1.0 minus X and then X and then X, so that Ka, which is 1.8 times 10 to the minus 5, is equal to X squared divided by 1.0 minus X. And of course that's approximately equal to X squared divided by 1.0, so that means X is going to be equal to the square root of 1 times 1.8 times 10 to the minus 5th, which is 0.0042. So the pH under these conditions is minus the base 10 logarithm of 0.0042, and that comes out to 2.37. So let's compare. Without the common ion in there, the pH is 2.37. With the common ion, the pH is 4.74. So the effect of the common ion is that it keeps the pH from dropping down as low as it normally would. The common ion effect suppresses the ability of this acid to produce H's in solution. Well, in buffers, we take advantage of the common ion effect to accomplish a certain thing. A pH buffer is a mixture of two solutes that controls the pH of a solution. So here are what the two solutes are. One of the components of a buffer is a weak acid. So HA, let's call it generically, which could be like acetic acid or hydrofluoric acid, any weak acid. And then the second component is a soluble salt that supplies the conjugate base of that same acid. So generically, we could say A-. For example, if we were using HF as our weak acid, we would have to have a salt like NaF that provided F-, the conjugate base. Mix those two together, and the common ion effect serves the purpose of limiting how much the equilibrium reaction can shift one way or the other. So here's a generic buffer setup. We have HA in equilibrium with H+ and A-. And now remember, we have a solution that has some of this and has some of this. Let's pretend that we add a whole bunch of excess H+ to the system. If I add a lot of H+ to the system, typically what would happen is the pH is going to start to drop. But with this buffer system in place, this H+ just causes a reaction shift to the left. So it uses up the H+ that you've added. It makes a bunch more HA and uses up some A-. So the ratio of HA to A- changes, but the amount of H+ that's present in the solution isn't nearly as much as it would be if you just dumped H+ into water. So it buffers the effect. The reaction shifts to the left, minimizing how much the pH gets lowered. By the same token, if I put a bunch of OH-, like I poured a strong base into this mixture, the H+ would immediately react with the OH- that I've added to produce H2O. And this reaction is going to be reversible, but not very much. It's going to be almost a straightforward reaction. So what does that do? Well, the OH- gets neutralized by taking H+ out of solution. The HA will respond by shifting to the right. This system will shift to the right and use up HA, producing H+ to make up for the lost H+, and also producing some A-. But the pH, which would normally take off, is now buffered. So by shifting to the right, it minimizes the increase in pH that would happen if you add a strong base. And so buffers are moderators. You can set the pH of a buffer at some amount. Let's say it was like 7. You add a whole bunch of H+. Instead of the pH dropping, it just drops a little bit. Stays pretty close to 7. Add a whole bunch of OH-, typically it would rise, but the pH just stays pretty close to 7. So that's the effect of a buffer. It's nice to know what is the pH of a buffer, and we can do that by just using a Rice chart. And then we're going to make a generalization from the Rice chart and come up with a powerful equation for solving a bunch of buffer problems and problems that aren't explicitly identified as buffer problems as well. So let's work out this problem. What is the pH of a buffer system that's 0.1 molar acetic acid and 0.015 molar sodium acetate? So we have acetic acid as our weak acid, and it's going to set up an equilibrium with H+ and acetate ion. And the acetate ion comes from our sodium acetate. Initially, the sodium acetate was 0.015 molar, so that means the acetate ion is also 0.015 molar. If you don't understand why that's true, talk to me in class. That's a 0, and this is a 0.10 molar acetic acid solution. So that's our initial concentration. And then here's our change. Once this whole thing dissociates, this is going to be minus X plus X and plus X, we'll say. So at equilibrium, this is 0.10 minus X, X, and 0.015 plus X. So Ka, which is 1.8 times 10 to the minus 5 for acetic acid, is equal to X times 0.015 plus X divided by 0.10 minus X. And 10 to the minus 5 is pretty small, so we're going to make the assumption that this is really the same as 0.015X divided by 0.10. X then is 0.10 times 1.8 times 10 to the minus 5 divided by 0.015. And if we solve for X comes out to 1.0 times 10 to the minus 7th, and that is equal to H plus concentration on our equilibrium chart. So the pH is 7 for this mixture, 7.00 I should say. Now we could make a generalization here. One of the things that we're going to see over and over again, we have been seeing this, is that this is always going to be a pretty small number. These are weak acids. A buffer by definition is made up of a weak acid and its conjugate base. So this assumption that we've made that we can drop the X in the numerator and drop the X in the denominator where it's added to the original concentrations, that's pretty much always going to be the case. And so we can generically say that we can drop that almost all the time. So let's set this up differently. Let's just make a universal weak acid, HA, in equilibrium with H plus and its conjugate base. And let's make a generic Rice chart. Initial concentration, no matter what it is, we'll just put down HA naught. Initial concentration of X, we'll say nothing. And the initial concentration of the conjugate base from the salt that goes in with it, we're going to call this A minus naught concentration. So our change, these are monoprotic, so it's 1-to-1. At equilibrium, we have the initial concentration of HA naught minus X, and the initial concentration of A minus plus X. But this is going to simplify almost every time to concentration of HA naught. And this is going to simplify every time to concentration of A minus naught. And we're going to drop those X's because these are weak acids and weak conjugate bases. The Ka's are always small. So we can develop this generic idea here. Ka is equal to concentration of H plus, that's going to be X, times concentration of A minus initial, divided by concentration of HA initial. That's a version of what's called the Henderson-Hasselbalch equation. So if we wanted to know H plus concentration, which is more common, we can isolate it from this equation. H plus is going to be equal to Ka times the initial concentration of the acid divided by the initial concentration of the base. So this is a simplifying tool. We can use this all the time if we want to know what the H plus concentration of any buffer is going to be, if we just know the concentrations of the acid and the salt that has the base. Now this can be taken a little bit further. We can take this equation and take the negative logarithm of both sides. So minus log H plus concentration is the left-hand side. And on the right-hand side, we have minus the log of Ka times HA concentration naught divided by A minus concentration naught. Well, minus log of H plus concentration is just pH. This could be rewritten as minus the log of Ka minus the log of HA naught over A minus naught because of our rules for logs. So we're going to introduce a new concept here, and that is pKa. Minus the log of anything is the P of that thing in chemistry. So minus log Ka is what we call pKa. So you just take the log of Ka, its opposite would be pKa. And then the other thing I'm going to do in my last step here is I'm going to make this a round. So I'm going to rewrite the Henderson-Hasselbalch equation this way. I'm going to say pH is equal to pKa plus the base 10 logarithm of A minus concentration initial divided by HA concentration initial. And now I have another version of the Henderson-Hasselbalch equation that's useful if I just want to know directly what is the pH. pKa values, you can figure them out, but you can also look them up. Most of the reference tables that give you Kas will also give you pKas. So then you just need to know what's the concentration of A minus and what's the concentration of HA when you start mixing the thing up. And that's usually pretty easy to figure out. But there's even another simplification that we can make. Because the A minus and the HA are both in the same mixture, they're both in the same volume, concentration is moles per liter, and the liters are just going to drop out. So in addition to this, we could write another version of the Henderson-Hasselbalch equation that gives us even more power. I'm just going to write it down here. pH is equal to pKa plus the base 10 logarithm of number of moles of A minus over number of moles of HA that went into the original mixture. And sometimes that's much more convenient than having to figure out the concentration. Sometimes you don't even know the concentration because you don't know the volume. But you can still figure out the pH of the buffer. So we have three different versions of the Henderson-Hasselbalch equation. One in terms of H+, that's this one. One in terms of concentration and pH, that's this blue one here. And then the purple one is in terms of mole quantities. They all mean the same thing and can be used to figure out what's going on with the buffer. So if you wanted to make a buffer, how would you prepare a buffer that has the pH that you want? Well, if you look at the Henderson-Hasselbalch equation, which is saying that pH is equal to pKa plus the base 10 logarithm of the concentration of A minus over the concentration of HA, or number of moles. If you made the ratio of concentration of A minus to concentration of HA in your initial buffer system equal to 1, then the log of that would be 0, because log of 1 is 0. And so that would tell you that pH is equal to pKa. So what you want to do is kind of get in the ballpark of your pH by finding an acid that has a pKa that's plus or minus 1 unit of the desired pH, the pH that you're shooting for. And then, this doesn't have to be 1. That ratio can be tweaked up or down to fine-tune the pH and get it right into what you want it to be, exactly at the target. So for example, let's answer this question. Could you create a pH 5.0 buffer using acetic acid and sodium acetate? Let's figure it out. Well, how we figure things out with buffers is with the Henderson-Hasselbalch equation. So it's pH equals pKa plus the base 10 logarithm of, we're going to say number of moles of acetate, because that's the conjugate base, over number of moles of acetic acid. And the pKa for acetic acid is equal to minus the base 10 logarithm of Ka, which for acetic acid, you've probably seen this before, so we've been using this as an example quite a bit, 1.8 times 10 to the minus 5, and pKa is then 4.74. So what we want to know is it possible to have a buffer that has a pH of 5.0 using this combination of acetate and acetic acid? Well, let's set to work by solving this equation for that ratio and then seeing how we could adjust and get at our target pH. First of all, this is a pretty good choice because our target pH is 5 and the pKa is within 1 pH point of our target pH. So that's a good choice. So how could we exactly make it? Well, if I subtract pKa from both sides, I'll find this. pH minus pKa is equal to the base 10 logarithm of number of moles of acetate divided by number of moles of acetic acid. So I can put numbers in here already. I know that my target pH is 5. I know that my pKa is 4.74. So the difference between that 5.0 and 4.74 is equal to this logarithm up here. So 5 minus 4.74 is 0.26. That would have to be equal to the base 10 logarithm of C2H3O2 moles over number of moles of acetic acid. To get rid of the logarithm, I can take 10 to both sides. So I'll do that. And that's telling me that 10 to the 0.26 is equal to the ratio of moles of acetate to moles of acetic acid. And 10 to the minus 0.26 is 1.8. So you can make this buffer by choosing acetic acid and acetate as your buffer system, and then just make sure that the ratio of moles of acetate to moles of acetic acid is 1.8. So 1.8 times as much acetate ion as there is acetic acid, and you'll have a 5.0 buffer. We have one more concept before we're done with discussion of buffers, and that is buffer capacity. It is possible to overpower a buffer. It won't continue to hold that pH forever. So buffer capacity is really answering this question. How much acid or base can the buffer absorb and still stay within the range that you need it to stay in? So it's the maximum amount. Buffer capacity is the maximum amount of acid or base that you could absorb and still not fall out of that given range. The best way to understand this is with an example. So we're going to look at this. If we have a liter of an acetic acid acetate buffer system, and it's made from 1 molar solutions of both, can this system absorb 0.15 moles of H plus without the pH changing by more than 0.1 pH unit? We can solve this problem by use of a Rice chart if we understand what's going on in buffers. Let's get to work. So let's first of all figure out what is the pH of this buffer system. pH for any buffer system is pKa plus the base 10 logarithm of the concentration of the conjugate base, which in this case is the acetate ion, divided by the concentration of the acid, which is acetic acid in this case. And we know we have 1 molar solutions of both, so pH is equal to the pKa of acetic acid, which in the last problem we saw is 4.74, plus the base 10 logarithm of 1.0 molar over 1.0 molar. Well, that term just goes to 0, so the pH of this buffer is 4.74 as it's set up. So the question is, we want to see if we can absorb 0.15 mole of H plus without drifting more than 1/10 of a pH unit away from pH 4.74. So if we do this, if we add H plus, the pH should drop, and we want to see if we can stay inside 4.64. That's our goal. If we can stay higher than 4.64, then our buffer has not exceeded its capacity. Well, let's look at what's happening, what's the equilibrium that's happening here when this buffer system is working. We've got H, C2H3O2, the acid, in equilibrium with H plus ions, and C2H3O2 1 minus. And this was created initially with 1.0 moles of acetic acid per liter and 1.0 moles per liter of acetate ion. And now we've added to this system 0.15 moles of H plus. What will happen? Well, here's the change that will take place. We've added a whole bunch of H plus, and the idea of buffer, how the buffer works, is it's going to shift to the right to use up virtually all of that H plus. The reaction is going to lie at equilibrium with H plus concentration at a very low level. So we can assume, for all practical purposes, that there won't be any H plus left, which means our change is going to be like this. We're going to lose 0.15 moles of H plus. But the stoichiometry is 1:1, so that means we also are going to lose 0.15 moles of acetate ion, and we're going to gain 0.15 moles of acetic acid. So that when we reach dynamic equilibrium, here's where we're at. We have 1.00 plus 0.15 moles of acetic acid. We're going to have virtually no H plus, and we're going to have 1.00 minus 0.15 moles of acetate ion. So this is, of course, 1.15 moles, and this is now 0.85 moles. So what's our new pH? Well, the Henderson-Hasselbalch equation will tell us that. So pH is equal to pKa, which we know is 4.74, plus the base 10 logarithm of acetate ion number of moles, and that's 0.85, divided by acetic acid moles, and that's 1.15. If you do this arithmetic, you come out to 4.61. So the answer is no. This buffer capacity is going to be exceeded by 0.15 moles of H plus because we have dropped more than 1/10 of a pH point. That was our target. Couldn't go below that, and in fact we did. So the buffer capacity has been exceeded, and no, it will not hold pH. Well, that's a lot of information, but it's also extremely useful information. So work on the practice problems and get good at this because it's going to serve you in good stead